Here is what happened the year before last, while most of us were scrolling past the headline without clicking. Someone found the tiny molecule that decides which of your genes actually switch on, a discovery now being aimed directly at cancer and genetic disease. Someone else built the mathematical ancestor of every chatbot and image generator you have used this year, and won a physics prize for it, despite never touching a telescope. Someone else used that very same technology to crack a 50-year-old biological puzzle, and in doing so handed medicine a shortcut that used to take a graduate student's entire doctorate. And a group of elderly Japanese survivors of the only nuclear attacks in human history spent 7 decades making sure the rest of us never forget why those weapons must never be used again, right as that very taboo is coming under fresh pressure. None of this stayed in the headlines for more than a day. All of it is already shaping your medicine cabinet, your phone's autocomplete, and the news you will read next year about artificial intelligence and nuclear risk.
So that is the pitch. Stick around, and by the end you will understand your own genes, the machine learning boom, and the nuclear question dominating global politics, better than most people currently arguing about them online.
And it starts fittingly with two scientists who spent decades staring at a genuinely unglamorous subject, a millimeter-long roundworm, and stumbled into one of the biggest discoveries in modern biology.
Welcome back. I am here with our host again, who has apparently developed new strong opinions, this time about worms.
Extremely strong opinions about worms, yes. Today we are covering all 6 2024 Nobel Prizes: medicine, physics, chemistry, literature, peace, and economics. Same format as before. Plain language explanations, real historical depth, and a direct line to the world you are living in today.
Fair warning, as always. 5 parts about 10 minutes each. This is a lecture, not a headline scroll. Get comfortable.
Or get a worm, if you happen to have one lying around, because that is actually where we begin. Chapter 1. The Instruction Manual inside the Instruction Manual. The 2024 Nobel Prize in Physiology or Medicine went to Victor Ambros and Gary Ruvkun for the discovery of microRNA and its role in what scientists call post-transcriptional gene regulation.
A phrase that sounds like it was designed specifically to end conversations at dinner parties.
Fair, so let us rebuild it from scratch. Every single cell in your body, your skin, your liver, your neurons, contains the exact same DNA, the exact same instruction manual. And yet a skin cell behaves nothing like a liver cell. The obvious question is, if they are reading from the same book, how do they end up as such different characters? For most of the 20th century, the accepted answer involved specialized proteins called transcription factors, essentially editors who decide which chapters of the DNA manual get read aloud in any given cell. That answer was correct, but incomplete, and Ambrose and Ruvkun, working independently in the 1990s on a roundworm called Caenorhabditis elegans, found the missing piece almost by accident.
Tell the worm story, because I know there is a worm story.
There is always a worm story. Ambrose was studying a gene in this roundworm called Lin4, and Ruvkun was studying a related gene called Lin14. Both men noticed something strange. Mutations in Lin4 seem to control the activity of Lin14, but nobody could find a protein that Lin4 was supposed to be producing to do that job. In 1993, Ambrose made the breakthrough. Lin4 was not coding for a protein at all. It was producing a tiny snippet of RNA, so small that most scientists at the time would have dismissed it as background noise, junk, a copying error. Ruvkun then showed exactly how this tiny snippet worked. It physically attached itself to the messenger RNA carrying instructions for building the Lin14 protein and effectively muzzled it, preventing the protein from ever being made.
Give me the version for someone who last opened a biology textbook in high school.
Imagine your DNA is a giant cookbook, and every cell in your body owns an identical copy. A skin cell and a liver cell both have the recipe for every dish in the book, but the skin cell only ever cooks the skin recipes, and the liver cell only ever cooks the liver recipes. Scientists already knew there were head chefs, the transcription factors, deciding which recipe cards get pulled out and read aloud in the kitchen. What Ambrose and Ruvkun found was a second, sneakier control system, tiny scraps of paper called microRNAs that float around the kitchen and physically stick themselves onto specific recipe cards, right after they have already been pulled out, jamming them shut before the ingredients can actually be measured and cooked. It is quality control happening after the order has already been placed, not before.
And for years, this was considered a strange quirk of one worm.
Exactly, and that is the great plot twist of this story. For roughly 7 years after the 1993 discovery, most of the scientific community treated it as a delightful but minor peculiarity of this one particular roundworm, a strange evolutionary side note. Then, in the year 2000, Ruvkun's laboratory discovered a second microRNA, called Let7, and this one was not confined to worms. It appeared in nearly identical form across flies, mice, and humans. That single finding transformed a worm curiosity into a universal biological principle. We now know the human genome carries well over 1,000 distinct microRNAs, quietly editing which genes actually get expressed in nearly every tissue in your body.
Real-world stakes, please, because a molecule silencing recipe cards is elegant, but I want to know why my body should care.
Because when this quality control system breaks down, the consequences are serious and specific. Mutations affecting microRNA production cause a condition called Dicer-1 syndrome, which sharply raises the risk of tumors across multiple organs in children and young adults. Abnormal microRNA activity is now recognized as a contributing factor in numerous cancers, since a cell that has lost its ability to properly silence certain genes can start growing uncontrollably. On the flip side, researchers are actively developing microRNA-based therapies, drugs designed to either mimic a missing microRNA or block an overactive one, for conditions ranging from certain liver diseases to specific cancers and even hearing loss caused by inherited genetic mutations.
So this is not ancient worm trivia. It is presently sitting in clinical trials.
Presently sitting in clinical trials and already shaping agricultural science too, since the same silencing mechanism is being engineered into crops to protect them from certain pests and viruses. There is also a genuinely everyday example worth mentioning, one that has nothing to do with a hospital. Every plant-based cooking oil you might see labeled as containing a modified fatty acid profile. Every disease-resistant crop variety bred using modern molecular tools increasingly leans on an understanding of exactly this kind of RNA-based gene silencing, sometimes called RNA interference. Farmers spraying a specific RNA-based treatment onto a field, rather than a broad chemical pesticide, to selectively shut down a gene inside a targeted pest insect while leaving every beneficial insect completely untouched, is a technology built directly on the foundation Ambrose and Ruvkun laid with a worm nobody outside their own laboratories had ever heard of.
Gary Ruvkun, reflecting on the scale of attention that comes with a Nobel Prize, noted that he had picked up plenty of prior awards over his career, but nothing remotely resembling this level of press attention, calling it a completely different world overnight. Here is the historical echo worth sitting with. For most of the 20th century, biologists operated on what was called the central dogma: DNA makes RNA, RNA makes protein, a tidy one-way assembly line. Ambrose and Ruvkun's discovery proved that assembly line has its own internal editors, small pieces of RNA that never become protein at all, yet control everything downstream anyway. It took nearly 7 years, and a second worm gene found halfway around the biological tree of life, before anyone realized this was not a quirky exception. It was one of the most universal rules in all of biology. From a hidden editor inside your own cells, we now move to a hidden mathematical structure inside your phone, borrowed, of all places, from the physics of magnets. Chapter 2: The Physics Prize That Went to Artificial Intelligence.
The 2024 Nobel Prize in Physics went to John Hopfield and Geoffrey Hinton for foundational discoveries and inventions that enable machine learning with artificial neural networks.
And I remember this one causing genuine confusion, because neither of these men study particles, gravity, or telescopes.
Correct, and that confusion was widespread. Plenty of physicists publicly wondered whether the Nobel Committee had simply gotten swept up in the artificial intelligence hype of the moment. But there is a genuinely deep, decades-old connection between physics and neural networks, and understanding it explains almost everything about the technology reshaping your life right now. In 1982, John Hopfield, a physicist, was thinking about magnetism, specifically about how the tiny magnetic spins of individual atoms in a material interact with their neighbors, all settling collectively into a low-energy, stable arrangement. Hopfield had an insight that this exact same mathematics of many small components pulling each other toward a stable, low-energy state could describe something entirely different: memory.
Explain that leap, because atomic magnets and memory sound like an enormous jump.
Think of it this way. Imagine a hilly landscape, riddled with valleys and a ball rolling around on it. Wherever the ball comes to rest in whichever valley represents one stored memory. Hopfield built a network of connected artificial nodes, mimicking simplified neurons, and mathematically arranged the connections between them so that specific patterns, like a face or a written digit, corresponded to those low-energy valleys. Then came the useful trick. If you fed the network a smudged, incomplete, or partially corrupted version of one of those patterns, the network would automatically roll downhill, node by node, correcting itself, until it settled into the nearest complete, clean memory. It could reconstruct a whole image from a fragment, purely by following the physics of energy minimization.
5-year-old version, please.
Picture a jigsaw puzzle that magically finishes itself. You hand the network a puzzle missing half its pieces, blurry, torn, incomplete, and instead of giving up, the network keeps nudging pieces around until the picture looks as much like something it has seen before as it possibly can, then locks into place. Hopfield built the mathematics that let a machine do that nudging automatically, borrowed directly from equations physicists had already been using for decades to describe how magnetic materials settle into their most stable state. Now, at the time Hopfield published this idea, Geoffrey Hinton was working at Carnegie Mellon University in the United States. He took Hopfield's network and pushed it a crucial step further, adding an element of randomness borrowed from statistical physics, specifically from the Boltzmann equation, which describes the probability of a physical system existing in different energy states. Hinton's version, nicknamed the Boltzmann machine, could do something Hopfield's original network could not. It could learn on its own, discovering hidden patterns and categories buried in raw, unlabeled data, rather than simply memorizing patterns it had already been explicitly given.
And this eventually scales up into the artificial intelligence boom we are all currently living through.
Precisely. Hinton kept refining these ideas through the so-called AI winters, decades where public and financial interest in neural networks nearly evaporated, and most of the computing world moved on to other approaches entirely. He persisted anyway, alongside a small handful of similarly stubborn researchers. Then, in 2012, a neural network from Hinton's own research group at the University of Toronto achieved a startling leap in image recognition accuracy at a major competition, a result widely credited with kicking off the modern machine learning revolution that eventually produced the image generators, voice assistants, and chatbots now sitting on your phone.
There is a wonderful, slightly chaotic detail about the actual phone call announcing this prize.
There genuinely is. Hinton took the call from a modest hotel on the American West Coast at roughly 3 in the morning local time, apologizing for the weak internet connection and mentioning, almost as an aside, that he now had to cancel a medical scan he had scheduled for that same day. A Nobel Prize announcement rearranging your actual doctor's appointment is a fairly on-brand way for this story to unfold. Here is a day-to-day way to feel the weight of this discovery. Every time your phone's keyboard predicts your next word, every time a streaming service recommends a show, every time you ask a voice assistant a question, and it actually understands you, some descendant of Hopfield's energy minimizing network and Hinton's pattern discovering Boltzmann machine is quietly doing the work underneath. None of that existed in any usable form as recently as the early 2000s. The gap between a curious 1982 physics paper about magnetic memory and a chatbot answering your homework question is really only one long, patient career of refusing to give up on an unfashionable idea.
Here is a broader historical parallel worth noting.
Physics has a long tradition of exporting its mathematics into completely unrelated fields. The equations describing heat diffusion were later repurposed to price financial options. The mathematics of fluid turbulence shows up in traffic flow modeling. What Hopfield and Hinton did was take equations built to describe atoms and magnetism and use them to describe learning and memory itself, blurring the line between a law of physics and a theory of mind. It is a reminder that the boundaries between scientific disciplines are often far more porous than the university department walls would suggest. There is also a sobering historical lesson buried in this story, worth sitting with for a moment. Neural networks fell dramatically out of fashion twice, in periods researchers now call AI winters, once in the late 1960s and again in the late 1980s, when funding agencies and university departments largely concluded the entire approach was a dead end. Hinton kept working on the same core ideas through both of those winters, at a time when doing so was, by most accounts, a genuinely unfashionable and professionally risky choice. It took roughly 30 years from his original Boltzmann machine paper to the 2012 breakthrough that finally convinced the wider field he had been right all along.
From physics borrowed for artificial intelligence, we move to chemistry, where artificial intelligence returned the favor and cracked a puzzle that had frustrated biologists for half a century. Chapter 3: 50 Years of Protein Guesswork, Solved in an Afternoon.
The 2024 Nobel Prize in Chemistry was split between David Baker, honored for computational protein design, and Demis Hassabis and John Jumper, honored jointly for protein structure prediction.
Two related but distinct achievements, wrapped into one prize.
Correct, and both concern the same basic biological object, proteins, the microscopic machines that carry out almost every function in your body, digesting food, contracting muscle, fighting infection, carrying oxygen in your blood. A protein starts life as a long, simple chain of building blocks called amino acids, but that chain immediately folds itself within fractions of a second into an intricate three-dimensional shape. That shape is not decorative, it is everything. A protein's shape determines its function almost entirely, the way a key's specific notches determine which lock it can open. For 50 years, starting in the 1970s, biologists faced an infuriating problem. Given a protein's simple amino acid sequence, predicting its final folded three-dimensional shape through calculation alone was almost impossible. The number of ways a single protein chain could theoretically fold is so astronomically large that brute force calculation was hopeless, and yet real proteins in real cells fold correctly, reliably, in a fraction of a second, every single time.
5-year-old version of the folding problem, before we get to the solution.
Imagine an impossibly long, wet piece of string, and you are told that if you drop it on the floor, it will always land in the exact same intricate knot, every single time instantly. Your job is to predict, just from knowing how long the string is, exactly what that knot will look like without ever actually dropping it. For 50 years, that was essentially impossible for computers to do reliably, for any protein humans had not already painstakingly measured in a laboratory, a process that could take years of a scientist's career for just one single protein.
And this is where the Google DeepMind team enters.
Demis Hassabis and John Jumper, working at Google DeepMind in London, attacked the folding problem using deep learning, the very technology Hopfield and Hinton's earlier work had helped make possible. Their first version, released in 2018, was promising but imperfect. Then, in 2020, they unveiled AlphaFold 2, and the results stunned the entire field of structural biology. The new system predicted protein shapes with an accuracy rivaling the best laboratory measurement techniques, in minutes, on a computer, for proteins nobody had ever physically measured before.
Give me the scale of what that actually unlocked.
By the time the Nobel Prize was announced, AlphaFold 2 had already been used by more than 2 million researchers across 190 countries, and the team had used it to predict the structure of virtually every protein humans have so far discovered, while mapping the genomes of organisms across the entire tree of life, something in the range of 200 million distinct protein structures. Something that used to require years of a single scientist's career, painstakingly growing crystals and firing X-rays at them, could now be done in minutes, for free, from a laptop. Demis Hassabis, on hearing the news, said simply, quote, "Receiving the Nobel Prize is the honor of a lifetime."
And David Baker's half of the prize runs in the opposite direction from prediction.
Exactly right, and this is the elegant symmetry of the prize. If Hassabis and Jumper answered the question, given this sequence, what shape will it fold into? David Baker answered the reverse question, given the shape I want, what sequence should I write? Starting in the early 2000s, Baker's laboratory at the University of Washington developed computational tools that could design an entirely new protein from scratch, one that had never existed anywhere in the history of life on Earth, and then reliably predict that it would fold into the exact shape the researchers wanted. His team has since designed proteins intended to function as vaccines, as tiny sensors, as novel nanomaterials, and even as light-emitting molecules invented from nothing but a chemist's imagination and a very capable algorithm.
So one half of the prize reads Nature's already written proteins, and the other half writes brand new ones nature never got around to inventing.
That is the whole story in one sentence. And the practical door this opens is enormous, faster vaccine design, custom enzymes that break down plastic waste or industrial toxins, therapies engineered atom by atom for a specific disease target, rather than discovered by years of trial and error screening through thousands of existing molecules, hoping one happens to work. Consider a very concrete, day-to-day version of the old way of doing things. Before AlphaFold, if a pharmaceutical company wanted to design a new drug targeting a specific protein, step one was often determining that protein's actual three-dimensional shape using a technique called X-ray crystallography, first developed in the early 20th century. That process could require growing a perfect crystal of the protein, a task so difficult and finicky that some proteins simply refused to crystallize at all, no matter how many years a graduate student spent trying. An entire drug discovery program could stall out for years on that single step alone. AlphaFold did not eliminate the need for laboratory confirmation entirely, but it collapsed that opening bottleneck from years down to minutes for the vast majority of proteins scientists care about. Here is a historical thread worth noting. The Protein Data Bank, an open, publicly shared library of painstakingly measured protein structures, has been quietly built up by scientists worldwide since the 1970s, decades before anyone imagined artificial intelligence would ever read it. Every single prediction AlphaFold makes is only possible because that public data existed first, freely available, patiently assembled one protein at a time by thousands of anonymous researchers over half a century. It is a rare, genuinely inspiring example of open scientific infrastructure, unglamorous and thankless for decades, suddenly becoming the essential fuel for one of the most celebrated breakthroughs of the 21st century.
From reading the shape of life itself, we now turn to something considerably heavier, a prize awarded not for a discovery, but for 8 decades of refusing to let the world forget a single morning in August 1940. 5. Chapter 4: The People Who Would Not Let Us Forget.
The 2024 Nobel Peace Prize was awarded to Nihon Hidenkaio, a Japanese grassroots organization of atomic bomb survivors, for its efforts to achieve a world free of nuclear weapons, and for demonstrating, through direct witness testimony, that nuclear weapons must never be used again.
Give listeners the historical foundation, because this prize only makes sense with the full weight of the history behind it.
In August 1945, The United States dropped atomic bombs on the Japanese cities of Hiroshima and Nagasaki. Approximately 120,000 people were killed immediately, with a comparable number dying afterward from burns and radiation sickness. An estimated 650,000 people survived the initial attacks, and in Japanese they became known as hibakusha, meaning, roughly, people affected by the bomb. For years afterward, their suffering was largely concealed, both by wartime censorship and by the simple discomfort of a nation trying to rebuild. In 1956, local survivor associations, joined by victims of nuclear weapons testing in the Pacific, formed a unified national organization, the Japan Confederation of Atomic and Hydrogen Bomb Sufferers Organizations, shortened in Japanese to Nihon Hidankyo. It became the largest and most influential survivor organization in the country, pursuing two goals simultaneously: securing support and recognition for survivors themselves, and ensuring that no other population on Earth ever experiences what they experienced.
Explain how a survivor organization actually shapes something as abstract as international policy.
Through the simplest, most powerful tool available to them, direct testimony. For decades, aging hibakusha have traveled to the United Nations, to international peace conferences, and into classrooms around the world, describing exactly what they witnessed and endured in specific, unflinching, personal detail. The Norwegian Nobel Committee credited this testimony with helping to build what is now called the nuclear taboo, an increasingly powerful global norm treating the actual use of nuclear weapons as morally unthinkable, regardless of any military justification offered.
5-year-old version of what a taboo like that actually does.
Imagine a rule that is not written into any single law, is not enforced by any single police officer, and yet almost everyone on the planet follows it anyway, because breaking it would make you the most reviled person in human history. That is what the hibakusha helped build, not through military deterrence, but through simply making sure every generation since 1945 has had to look directly at photographs, and eventually hear directly from survivors, about precisely what a nuclear weapon does to actual human bodies, actual children, actual families. The Nobel Committee's own framing was blunt, that no nuclear weapon has been used in war for nearly 80 years, and that this survivor testimony deserves real credit for that fact.
And the committee was careful to frame this as a warning as much as a celebration.
Very much so, and this is worth stating plainly, without taking a side on any specific nation's current policy, simply as an accurate account of what the committee itself said. At the time of the award, the committee noted that nuclear-armed states were actively modernizing and expanding their arsenals, that additional countries appeared to be pursuing nuclear weapons capability, and that explicit threats to use nuclear weapons had recently been made in the context of ongoing wars. The average age of a hibakusha at the time of the award was over 85. The organization's own leadership has been candid that they do not know how many more years they will have enough surviving members to continue this work in person.
Which is precisely why the timing of this particular prize felt so charged.
The organization's own co-leader, Hiroshima survivor Toshiyuki Mimaki, reacted to the news with open astonishment, saying, quote, "Never did I dream this could happen." The committee chair, in turn, stated plainly that these historical witnesses have helped generate and consolidate widespread global opposition to nuclear weapons by drawing directly on their own personal stories rather than abstract policy argument.
Give us one historical parallel to anchor this.
Consider that this was not the Nobel Committee's first attempt to spotlight this exact issue. In 2017, the Peace Prize went to the International Campaign to Abolish Nuclear Weapons, an advocacy coalition working toward a global treaty banning nuclear weapons entirely. Awarding a second, related prize just 7 years later, this time to individual survivors rather than an advocacy coalition, signals a committee that views the danger as not merely persistent, but actively intensifying, and views first-hand human testimony as a tool at least as powerful as any treaty text.
From the heaviest possible subject matter, we move to two prizes that, in their own very different ways, are both about survival, one through fiction, and one through cold, hard economic data. Chapter 5: Why Words Endure and Why Nations Divert.
Let us close with literature and economics, two prizes that turn out on inspection to rhyme with each other rather nicely. The 2024 Nobel Prize in Literature went to the South Korean author Han Kang, cited for her intense poetic prose that confronts historical traumas and exposes the fragility of human life.
Give listeners a sense of her body of work.
Han Kang became the first South Korean writer and the 18th woman ever to win this prize. Her international breakthrough came with a novel called The Vegetarian, in which a woman's quiet decision to stop eating meat spirals into devastating consequences for her entire family, a book that also won the International Booker Prize in 2016. Her novel Human Acts, set in the city of Gwangju where she grew up, directly confronts a 1980 massacre carried out by the South Korean military against civilian protesters, giving voice to victims of a historical trauma her own country spent years trying not to discuss openly.
The Nobel Committee used a striking phrase, a double exposure of pain.
They did, describing how her writing repeatedly overlays mental and physical suffering onto one another, and connects the living to the dead with what one committee member called both a tender and a brutal lyrical style. In her own words, describing her long-standing preoccupation across multiple novels, she has said that she is essentially always questioning humanity's capacity for violence, and whether refusing that violence is even possible, and hopes readers will end up sharing that same open question rather than a tidy answer.
When the news reached her, by all accounts, it was a remarkably ordinary evening.
Genuinely ordinary. She had just finished supper with her son when the Swedish Academy reached her by phone, and she said simply that she was surprised and honored, and that she planned to celebrate quietly with tea. A striking contrast to the enormous historical weight of the subject matter she actually writes about.
Now for our final laureates, from a novelist confronting national trauma to economists explaining why some nations end up rich and others end up trapped.
The 2024 Nobel Prize in Economic Sciences went to Darren Acemoglu, Simon Johnson, and James Robinson for studies of how societal institutions are formed and how they affect prosperity. Here is the puzzle they spent decades untangling. The richest fifth of the world's countries are now roughly 30 times richer than the poorest fifth, and that gap did not always exist in anything like its current form. The three laureates went looking for the actual mechanism behind that divergence and found an unusually clean natural experiment sitting in plain sight: the historical record of European colonization.
Explain the mechanism, because at first glance colonization does not sound like a controlled scientific experiment.
It is not a clean laboratory experiment, but the historical variation is remarkably instructive. The laureates found that in regions where European colonizers could not easily settle in large numbers, often due to disease environments that were lethal to European populations, colonizers tended to establish what the laureates call extractive institutions, systems built purely to extract resources and labor for the colonizers' benefit, with little regard for long-term local development. In regions that were safer and more attractive for European settlers to build permanent lives, colonizers were more likely to establish inclusive institutions instead, protecting property rights and broadening political participation, because the colonizers themselves intended to stay and prosper there personally.
And the truly startling finding is how those choices, made centuries ago, still echo today.
This is the part that should genuinely surprise you. Some regions that were relatively wealthy and densely populated before European colonization ended up with the more extractive institutions imposed on them, precisely because their existing wealth and population made extraction more immediately profitable for the colonizers. Those same regions, in many documented cases, are relatively poorer today. Meanwhile, Regions that were sparsely populated and looked unpromising at the time of colonization often received more inclusive institutions because colonizers intended to settle there permanently, and those regions frequently rank among the wealthier nations today. In a great many cases, the historical ranking has been almost completely inverted over the following few centuries.
Give me the 5-year-old version of why an old institutional choice would still matter hundreds of years later.
Imagine two neighboring farms are handed down through many generations of families. On one farm, an old family rule guarantees that whoever plants a crop gets to keep and sell it themselves. On the neighboring farm, an old family rule instead says the local landlord takes whatever is grown, no matter who planted it. Even after every single original person on both farms has long since died, the families still tend to follow whichever rule they inherited, because that is simply how things have always been done there, and each rule shapes whether new generations bother working hard, investing, and innovating, or simply give up trying. Semiglu, Johnson, and Robinson essentially prove that entire nations behave the same way, carrying forward institutional habits established centuries ago by the specific choices of long-dead colonial administrators.
And this obviously is not just a history lesson about the distant past.
Not remotely. Darren Asemoglu, discussing the implications of the research directly, stated plainly that for the long-term health of any nation's economy, there is probably nothing more important than the health of its institutions, and that any leader who damages them should be considered the single greatest economic risk a country faces. His co-laureate Simon Johnson made a related point, that democratic systems have to actually deliver shared prosperity to their citizens, or people understandably begin to question the legitimacy of the entire system itself.
Which sounds like it is speaking rather directly to arguments happening in more than one country's politics at this very moment.
Precisely, and that is exactly the enduring power of the research. It reframes prosperity as neither an accident of geography nor an accident of culture, but as a direct, traceable outcome of specific, changeable institutional choices, choices that were made deliberately in the past, and can, at least in principle, be made deliberately again in the present.
So let us zoom all the way back out, because once again, we have covered enormous ground.
We have a microscopic scrap of RNA discovered inside a laboratory roundworm, now guiding cancer treatment and gene therapy. A set of equations borrowed from the physics of magnets, now running the artificial intelligence transforming nearly every industry on Earth. An AI system that cracked a 50-year-old biological mystery in an afternoon, alongside a parallel technology that writes entirely new proteins nature never got around to inventing. A group of aging survivors of the only nuclear attacks in human history, using nothing but their own testimony to help build a global taboo now facing renewed pressure. A Korean novelist insisting that historical trauma and physical fragility deserve unflinching, poetic attention rather than comfortable silence. And three economists who trace the wealth gap between nations back to specific institutional decisions made centuries ago, decisions whose consequences are still being felt today.
If there is one thread connecting all 6 2024 prizes, what would you call it?
I would call it this. Every one of this year's laureates found meaning, structure, and consequence hiding inside something the rest of us had already decided to overlook: a boring worm gene, an old idea from magnetism, a stubborn 50-year-old biology problem, the testimony of elderly survivors, a difficult novel about historical violence, and the dry statistical record of colonial administration. None of it looked urgent from the outside. All of it turned out to be foundational. The physicist Richard Feynman once said that the first principle is that you must not fool yourself, and that you are the easiest person to fool. This year's laureates spent decades refusing to look away from evidence that seemed, at first glance, too small, too strange, or too painful to matter. And in every single case, that refusal changed how the rest of us understand ourselves.
And on that note, we will let you go. Thank you for spending 50 minutes learning why your cells edit their own instructions, why a physics prize went to artificial intelligence, why a 50-year-old biology problem finally cracked, why a group of elderly survivors just might be the reason nuclear war has not happened again, and why some nations got rich while their neighbors did not.
Until next time.